Okay, welcome back. This is what we did in the last class, mesh current method. Okay, in the last week and this week, what we did was to look at the node voltage and mesh current method. Let me quickly summarize the steps involved in the node voltage and mesh current method. Okay, this really is node voltage and mesh current method. Okay, so this is what we did in the previous classes, node voltage method and mesh current method. Okay, when you're solving using node voltage method, and we are going to look at one problem today. Okay, when we are solving using node voltage method, the first step is to select a ground node. Then we identify the different nodes and define voltages. Okay, and then set up KCL at each node. Once we set up KCL at each node, it's a matter of solving a system of simultaneous linear equations. Okay. And how about the mesh current method? Mesh current method begin by identifying all the independent meshes. Okay, what's a mesh? Let me remind you. Mesh is still a loop. Mesh is a subset of a loop. A mesh is a loop that does not have any other loops in it. Okay, so once we have identified all the meshes, we annotate the reference mesh currents. Okay, we annotate the reference mesh currents and set up equations using KVL around each mesh. Okay.
Hey, Professor.
Yes.
I'm sorry to interrupt. I don't know if it's just my screen, but I actually don't see what you're working on with the whiteboard.
Better?
Thank you.
Perfect. Sorry about that. So here is the summary of node voltage and mesh current method. When we are solving using node voltage method, there are 3 steps: selecting the ground node, identifying the node voltages and defining currents, and then setting up KCL equations at each node. Once you do that, it's a matter of solving a system of simultaneous linear equations. How do you do the mesh current method? Similar, but we dabble in currents. Okay, we identify all the meshes, we set up reference directions for currents, and then set up equations using KVL around each mesh. Okay, let's see if we can solve. These are the general steps that we looked at in the last class. We solved a couple of example problems. I want to spend some more time solving one more problem for each. So here's what we're going to do. We'll take this circuit, okay, and try to solve it using mesh current method. Okay, so if you do using mesh current method, you're solving for different currents. Okay, so there is I1 you're trying to find, I2, I3, all the different currents, all the different branch currents. Okay, this is what we'll be doing using the mesh current method. Okay, then we take the exact same circuit. Okay, we take the exact same circuit and solve it using node voltage method. Okay, let's see. Let me go further down. We solve the exact same circuit using node voltage method and still try to find the values for these currents. Okay. Using the node voltage method, if we did the problems correctly, we should end up with the exact same result, right? The I1 calculating using node voltage method or the mesh current method, it should yield us the exact same results. Okay, so here is what the node voltage method will entail. We'll identify the different nodes. What are the different nodes? What is a ground node? I choose to use this guy as ground. Okay, you could use any other node as a ground and still arrive at the exact same answer. Okay, it does not matter. The reference node that you pick does not matter as long as you're consistent with it. Okay, so I pick this guy as my, I pick that guy as my reference node. Okay, and identify several other nodes. Okay, let me call this node 1 with a voltage of V1. Let me call this node 2 with a voltage of V2. And the one down below is node 3 with a voltage of V3. Okay, so when we are solving using node voltage method, the first result that we will see, or when you set up the equations, is that the equations are all going to be in V1, V2, and V3. So you have three equations. There are three nodes here. So there's going to be some equation in V1, V2, V3, and another equation, and then a third equation. Okay? Three equations. Once we get the values, so the unknowns here are V1, V2, V3. Okay? Once we find the values for V1, V2, and V3, it should be able to find the value for any current. Let's say you want to calculate the current I5. Well, I5 is simply V2 minus V3 over 12 ohms. Ohm's law, right? Similarly, if you want to find the current in any other branch, I don't know, let's pick I1. I1 would simply be 125 minus V1 over 1 ohm. Okay, so in other words, when you're solving using node voltage method, the first result that you see are all the node voltages. That explains the name, node voltage method. The result, the solution is in terms of node voltages. Then you have to solve for the different branch currents. Okay, let's see the other method. Let's look at the other method. Okay, let's see if we can go back here. Okay, and I'm going to get you started on this. Okay, by identifying the meshes. Okay, we want to solve this problem using mesh current method. Okay, let me say, let's see, there are three meshes in here. I'm going to call this guy as mesh 1. Okay, there's another guy. There's a mesh that's like so. Okay. And then there's the third one. Okay. Let me set up a reference current. So the first step is to identify the meshes, right? So if I go back to the summary again, when we are solving using mesh current method, the first step is to identify all the methods. We did that. The next step is to set up reference mesh currents. Okay, let's set up reference mesh currents like so. Okay, the first mesh, okay, let's see, the first mesh has a reference current of IA, like so. Okay, let me do the second mesh as well. I'm going to call this reference current as IB. Okay, let's do the third guy as well, which is IC. Okay, so the second step is done as well. I set up reference currents. Okay, so even before we embark on solving this problem, let's see what we expect to see. I expect to see three equations. There are three meshes, so I expect to see three equations. So an equation in terms of IA, IB, and IC, and another equation with the different variables, or not with different variables, but with different coefficients. Okay, and then the third one in IA, IB, IC as well. So when I set up the mesh current equations, I'm going to see three equations in IA, IB, and IC. And when I solve these equations, I'm going to get value for IA, IB, and IC. Once I have those, I should be able to calculate I5. Okay, what is I5 in this case? I5 is IB minus IC. It's the current flowing through the 12 ohm resistance. IB is the pink current flowing down in the clockwise direction. And then IC is the current going up in the clockwise direction. So I5 is IB minus IC. Okay. Similarly, if you want to calculate any other current, let's say you want to calculate I6. I6 is simply IC. Okay. If you wanted to calculate I1, okay, it's the current flowing here. I1 is simply IA. Okay, because it's not, this branch is not shared between any meshes. Okay, this branch is not shared between any meshes. How about I2? I2 is IA minus IB. So IA, so the current flowing westbound, the westbound current is a component of IA is flowing west. Similarly, a component of IB is flowing east. So the difference of these two will give you, I2. Okay, everybody with me?
Yep.
Okay,
Yes.
so let's see, good. Let's see if we can continue this problem. So once we have IA, IB, and IC, you should be able to solve for the different currents. Okay, so I want to leave this as an exercise for you. Why don't you take about 5 minutes or 10 minutes to set up the equations here? Okay, you start by writing KVL. Okay, KVL. around mesh number 1. So that's IA, right? So this is mesh 1. Okay. Then you would go about writing KVL around mesh 2, which is this guy, mesh number 2, shown in pink. So KVL around mesh number 2. Okay. Then you would go about writing KVL around mesh number 3, which is this guy. So let me clear some of these off. Okay. And pull them up just so you can begin working on the problem. Okay, so set up 3 equations, 1, 2, 3, using the KVL around each of these meshes. Take about 10 minutes to do that while I mute my microphone temporarily. Okay, let's begin working on this problem. Who can get us started on this guy?
I just finished the equations.
Okay, that's great. Yeah, why don't you get us started?
Okay. So setting up the KVL for mesh IA.
Okay.
So I had a voltage rise, so I put negative 125, and then just IA times for the 1 ohm resistor, and then I put is IA minus IC. So then through the next 6 ohm resistor, it would be 6 times IA minus IC. And then for the final resistor in that mesh, I would have 2 times IA minus IB.
All of that equals to 0.
Yeah.
All right. Perfect. So how about the second equation? So this is correct.
Okay. So for the second one, we have another voltage drop or voltage rise, so negative 125. And then I put for the 2 ohm resistor 2 times IA minus IB.
IA minus IB. I'm going to write it as IB minus IA
Oh, is it IB
times 2
minus IA?
ohms.
Okay.
That's a good point. The reason is, thank you for bringing that up. When I'm looking at the second loop, mesh right here, what's my reference direction? That's my reference direction. So I forget, I have to ignore what my earlier mesh was. When it comes to this mesh, writing this mesh equation, my new reference direction is this guy. Okay, so IB is aligned with my reference direction. IA is opposite to my reference direction. Okay, so depending on the mesh, each mesh has its own reference direction. So I'm going to write IB minus IA plus 2 ohms. And then did you have the third term as well?
Yeah, so then I think that would mean, so it would be 12 IB minus IC then?
Correct. IB
Okay.
minus IC times 12, because when I'm trying to look at the current flowing in the 12 ohm resistance, what's my reference current? You see it's shown in the pink here. It's clockwise. That's IB. Going down is IB. What's the other current going up in the opposite direction? IC. So if I have to look at the reference direction and annotate the currents. There is one current IB that is aligned with my reference direction going south, and there is one current IC that is opposite to the reference current direction. That multiplied by the resistance of this guy gives me the voltage dropped in this resistance. Okay, so that's how I solve it. That's how I write an equation for it. Okay, correct. And then did you also want to write the expression for the current in the third or the fourth element, the 1 ohm resistance?
Sure. So for that one then, just making a correction to my current mistake earlier, would so for the 12 ohm resistor, I have 12 times IC minus IB?
IB minus IC.
IB minus IC, okay, because it's going the opposite direction of I5.
Correct.
Okay.
It's going in the opposite direction of IB. Okay, don't worry about I5. I5 is just there because it's a branch current. I don't care about it right now. I'll come back to talking about it. So I can almost, ignore this guy. Okay, the only thing that I want to see is that IB is the current that I defined as a reference current, IB, right? IB is my reference current that I set up. Okay, so when I'm going along this direction of IB is positive. And what is the current going in the opposite direction to that in this 12 ohm resistance IC? Okay, so in other words, if you're looking at any circuit element, okay, at this 12 ohm resistance, what is the net current flowing in? Okay, there is one current. What's the net current flowing? There is one current IB going this way. There is one current IC going that way, right? IC, the brown current, is going in the opposite direction to IB. Okay, which one is positive and which one is negative depends on the mesh that we are solving. Okay, I'll explain that again when we look at 6 ohm resistance.
So I5, in this case, you put I5 equals IB minus IC just because of the KCL then?
Just because of the, let's see, let me clear this to show I5. I5, if you look at I5, so when I look at the 12 ohm resistance, okay, there is one current IB, this guy, the pink current going south, and there's one current going north, IC. So the net current I5 in this 12 ohm resistance is the difference between the two, IB minus IC, which is the difference of the two currents.
Okay.
Okay. We'll talk about that when we look at the 6 ohm resistance. Okay. Did you have other questions?
Nope, thank you.
Okay, so we almost finished the equation for the pink mesh number 2. There is one more voltage drop that I have to take into account, okay, which is the voltage drop through the 1 ohm resistance. That will be IB times 1 ohm, right? Equals to 0. Correct. Let's set up the KCL for mesh 3, KVL around mesh 3 as well. Okay, so let me try to explain this in a different manner to try and drive home the point in a different method. Okay, when we are writing the KVL around this loop, okay, all I'm trying to do is to add up the voltage dropped. Okay, I want to add up the voltage drop across each of these resistances along this path. When I follow this path, okay, I want to add up all the voltage drops. Okay, what's the voltage dropped in this guy, plus the voltage dropped in this guy, plus the voltage dropped in this guy. Okay, if I add up all the voltage drops around a loop, that should equal 0. That's the fundamental premise of KVL, right? So in order to understand the voltage dropped across this resistance, 12 ohm resistance, okay, what's the voltage dropped across 12 ohm resistance? Well, in order to be consistent, what I do is I'm using IC as my reference current and the reference direction. Okay, so in other words, if you look at this 12 ohm resistance, that's shared between the brown mesh and the pink mesh, right? This 12 ohm resistance is part of the brown mesh on the right and the pink mesh on the lower left. Okay, so in other words, two of these meshes are actually affecting the current in this 12 ohm resistance. Okay, how about this guy, 24 ohm resistance? That's not shared between any of the meshes. That is exclusively, completely in the mesh number 3, the brown mesh. Okay, so a small differences that we have to account for. Okay, so the net current that is flowing in the 12 ohm resistance here is the difference between what is supplied by the pink loop and what is supplied by the brown loop. Okay, so in other words, if I have to write the value for I5, that will be IB minus IC. Okay, what is supplied by the purple? Because I5, that's the current flowing in the 12 ohm resistance, is shared between the pink mesh and the brown mesh. Okay, so the current flowing in here, the current flowing I5 is IB minus IC. Okay, so if you were to write the voltage drop across the 12 ohm resistance, that will be the voltage dropped across the 12 ohm resistance is, excuse me, sorry. So voltage dropped across the 12 ohm resistance would be R times I with a plus and minus in this fashion. Okay, so there's a voltage drop of that guy, plus and minus V12. So now when you go about setting up the KVL around the brown mesh, there's a voltage gain. So you would include a negative in there. Okay, so in order to incorporate all of that, I'm simply going to follow the reference current from IC. Okay, so when I'm setting up the mesh current for IC, KVL equation for mesh number 3, I start at the lower left corner, okay, and see which current. So the first element that I see is the 12 ohm resistance. In the 12 ohm resistance, I know there are two currents. There is one current coming from this mesh 3, and then there is one current coming from, there's one current coming from this purple branch, IB, right? So the net current that is flowing in the 12 ohm resistance is the difference between IB minus IC. Okay, so if I'm writing the loop equation in loop B, I make IB as positive. If I'm writing the loop equation in loop C, I make IC as positive. Does that make sense? I'll give you another example. Let's see the example for the 2 ohm resistance. Okay, let's see the example for the current in the 2 ohm resistance here. That's shared between the blue mesh and the pink mesh, right? The 2 ohm resistance is shared between the blue mesh and the pink mesh. Let's look at the component of current that I am writing, the expression for current that I'm writing for the 2 ohm resistance appears like so: IA minus IB times 2 ohms. So when I'm writing the KVL around the blue mesh, I make IA as positive because that's my reference direction. Okay, the exact same term in the next equation. Okay, in the next equation, look at this guy. What did I do? I did IB minus IA times 2 ohms. So this is the current that's flowing in the 2 ohm resistance. I considered it as IB minus IA times 2 ohms. Okay, I don't want to belabor this point and confuse you more. I'll just illustrate the point using the example. Okay, all you want to remember is this 12 ohm resistance, when you're including it as a part of the purple loop, IB comes in the positive form and IC comes in the negative form. Okay, this 12 ohm resistance, when you're including it as a part of the brown loop, then IC comes in the positive form and IB comes in the negative form. Okay, let me write the equation out. So I'm going to use a thick marker. I'm writing the KVL around mesh 3. I start in the lower left corner. Okay, and my reference direction is this guy. That's my reference direction. Okay, so what would be the voltage dropped across the 12 ohm resistance? 12 times IC minus IB. Okay, plus, look at the 6 ohm resistance on the top. I'm going to multiply 6 ohms by IC minus IA. Okay, plus, now I pass the 6 ohm resistance and arrive at the 24 ohm resistance 24 times IC. That's all there is to the equation. All of that is 0. Let's see, let me cut that over there and paste it over here. Does that make sense?
Yep, looks good.
Okay. So I have 3 equations set up using the KVL around mesh 1, mesh 2, and mesh 3. Let me see if I can simplify these equations. When you simplify these equations, you're going to get something like this. Okay, you're going to see something like IA times 9 plus IB times negative 2 plus IC times negative 6 is 125. That's equation 1. Then IA times negative 2 plus IB times 15. Number 2. And number 3 is IA times negative 6 it should really have been 42. So I have 3 equations, 3 unknowns. I can solve it using MATLAB. Questions, please. Questions so far?
I think when I solved this in MATLAB, I got decimal values for my currents, and we don't
Yes.
usually get decimal values, but I guess, is that acceptable?
Yes, that's completely fine. If you're looking at numbers around 23.756, is that a value that rings a bell? So you have, did you go to the step of solving for whatever values you got for IA, IB, and IC? One of these should be, let's see, 23.756. IB should have been 18.428, and IC should have been 8.659.
Okay, yeah, that's what I got. Thank you.
Okay. Yep. So from here, it's a matter of finding I1, I2, and I3. Okay. Let's see. This is IA, IB, and IC. Okay, IA, IB, and IC. So once you have IA, IB, and IC, you should be able to use this to calculate I1, I2 through I6. That's what you're after, right? So I1 is IA. Similarly, I6 is IC. And then I3 is IB. So you should be able to get values for the different currents. Does that make sense? So let me give you the expressions. I1 should be IA, okay? And then I2 should be IA minus IB. I3 should be, that's the current flowing in the 1 ohm resistance, should be IB, okay? I4 should be IA minus IC, okay? IA minus IC. I5 should be, what's I5? IB minus IC. And then I6 should be IC. Okay, so using this relationship, let's see, using this relationship, we should be able to calculate the different branch currents. Does that make sense?
Yes.
Okay, let's see.
Professor, I have a quick question.
Yes.
So, does this mean that if it doesn't matter if I put I5 equal IC minus IB or IB minus IC, does it make any difference? Because now we are taking I5 from the IB world, right? Like putting IB positive and IC negative. So,
Correct. It does matter. It does matter because, see, what is the direction of I5?
downward. Okay.
Downward, going south, right?
Mm-hmm.
And that is along IB. What is the direction of IB?
Oh, okay. So same direction. Okay.
Yes. So for
Okay.
example, let's look at, I don't know, I2. What's going on with I2?
Oh, okay. So it has the same direction as IA, and that's why. Okay.
Correct. And that's why IA is positive and it has the opposite direction of IB, therefore IB is negative.
Oh, okay, I see. Perfect. All right, thanks.
Okay. Yep. That's a good question. Thank you for participating. Other questions, please. Okay, so that's a mesh current method. Mesh current method. I1 is IA. Okay, so good. So let's solve the exact same problem using node voltage method. Okay, node voltage method. Let's see, we have about 45 minutes of time. So let me write out the answers that you should have seen. Okay, when you solve for I1, I2, I3, I4, I5, and I6, these are the results that you should have seen. I1 should have been 23.7567, and decimal numbers are completely acceptable. I2 should be 5.3286 amperes. I3 should be 18.4281 amperes. I4 be 15.0977, 9.7691, okay, 8.6590 amperes. Okay, so these are the values for different branch currents that you should see. Okay, let's see if we get these results, the exact same results from the exact same circuit, if we use the node voltage method instead. Okay, let's see if we can use the node voltage method. Okay, node voltage method. I'm going to clean this up. Okay, for the node voltage method, okay, I got you started on the different steps, right? I got you started on the different steps. The first step is to identify a ground node, which we did. We identified the ground node. Just give me 1 second. Now, that's the ground node. The second step is to identify the different individual nodes. That's the second step. The third step is to apply KCL at each of these nodes. Okay, that's the step I want to leave as an exercise for you. Okay, let's see. V1, V2, V3. Why don't I KCL at node? Let me color code them carefully. I'm going to call this guy as okay. I'm going to color code this using blue. Okay, and then this guy is, I leave it as pink, and this guy I want to color code as I don't know. Okay, there are 3 nodes here. Okay, let's try to write the KCL at node V1. Then we'll write KCL at node V2. And then we will write KCL at node V3. Okay, so that's step number 3. Step number 1 and 2, I already did that for you. Now, why don't I get you started, because it has been almost a week since we spent some time on the node voltage method. I'll get you started on one of these equations. Which one would you want me to do?
How about V3?
V3. Okay, I want to write KCL at V3. So what I do is to look at all the currents that are coming in or going out. Okay, so there is one current going out, I3, and there are two currents coming in. So KCL here is going to be the current leaving equals to the currents entering. All right, so that would be my equation. Or I could even do it this way. The currents leaving, I3 is leaving, I5 is entering, so negative I5 is leaving. I6 is entering this node V3, that's the green node. So I6 is entering, so negative I6 is leaving. So when I sum all the currents leaving the node, it should equal 0. Or I could simply say this sum of currents entering, I5 and I6, equals to the sum of currents leaving. Okay, whichever one, it does not matter. It's exactly the same result. Okay, that's this guy. I3 is I5 plus I6. Let's see if I can put that in equation form. What's I3? I3 is the voltage here minus the voltage there over 1 ohm. Therefore, I3 is voltage on the right is V3 minus voltage on the left of the 1 ohm resistance is negative 125 volts over 1 ohm. That's this current. Okay, that's this guy, let's say. That's I3. Okay, then let's equate that to the currents entering. What's the current entering? I5, which is V2 minus V3. So I5 is the, let me clean this up, is the current going south, which would be the voltage here minus the voltage there by 12 ohms. Okay, so which is V2 minus V3 over 12 ohms. That would be this current. Okay, the current going south is this guy. But there's a third current here. There's a third current going in here as well, which is this guy. Okay, so I want to write an equation, expression for that as well. What would that be? That would be the voltage on the top minus the voltage on the bottom by 24 ohms, which is V1 minus V3 over 24 ohms. Okay, so that's KCL at node V3. KCL at node V3. So V3, there are three branches of currents. There is one in the yellow, one in the cyan, and one in the red, which are annotated here. Okay, there are three branch currents. V3 minus of negative 125 over 1 ohms, V2 minus V3 over 12, and then V3, V1 minus V3 over this guy. Okay, questions please, questions so far. Okay, so if you do not have questions, what I want you to do is to get started on writing KCL at node V1 and KCL at node V2. Take about 10 minutes to set that up. And if you're done with that and you still have time, you can go ahead and continue solving for V1, V2, and V3 by plugging it into your MATLAB. Okay, 10 minutes. Okay, let's begin. Let's continue where we left off. So we were trying to set up equations. So any volunteers to get me started? Any volunteers to set up equation for node V1, KCL at node V1?
I set up the equations, but I'm not entirely sure if I did it the same way.
That's fine. How did you do for node 1?
Okay, so for node V1, what I got is V1 minus 125 over 1 ohm resistance,
Yes.
plus V1 minus V2 over 6 ohm resistance, plus V1 minus V3 over 24 ohm resistance is equal to 0.
Perfect. Okay. So all you're doing is they're essentially the same. What I do and what you do are essentially the same. In a sense, what I do is I1 equals to I4 plus I5. So instead of adding all of them to 0, I just put them on two different sides of the equations and call this guy as, all I do is this, okay? Put it like this, okay? So add these two on one side and add this guy on the other side with a negative sign, okay? But what you do is essentially the same, okay? Except that you're all adding them on, you're adding all of them up on one side, okay? And then equating to 0. Perfect. So that's equation 2. Do you want to do the second equation as well?
Okay. So for node V2, I got V2 minus V1 over 6 ohms plus V2 over 2 ohms
Correct.
plus V2 minus V3 over 12 is equal to 0.
Perfect. All of that equals to 0. So why don't I rearrange this guy as well, V3, in a format that you like? Okay, in a format that you like, V3. The third one is going to be this guy. Let's see if I can add a page here. Add a page. Okay, this V3 minus negative 125 over 1 ohm plus V3 minus V2 over 12 ohms plus V3 minus V1, V3 minus V1 over 24 ohms. All of that equals to 0. In other words, these two equations are necessarily the same, okay? Just that they're on two sides of the equality sign, okay? 3 equations, 3 unknowns. I should be able to find the value for V1, V2, and V3, okay? Did you see a value for V1 to be 125? Let's see. Let's see. The values that you should have seen should be V1 is, everybody with me so far? Setting up the equations?
Professor, just a quick question.
Yes.
So for the node that V2, I'm just a little bit confused about the, I know that you choose the ground like as a reference, but I thought that this is just for the like mesh method. It's so I mean, why it's not 125? Why it's 0? Like, I'm just
Why
confused.
it's not 125? Why it is 0? Okay,
Mhm.
so this is where I begin as my reference. I choose that as my reference. Okay, so in other words, um, let's say you're trying to compare the height of 3 people, 5 people. Okay, I'm trying to compare the height of 3 people. Person 1, 2, 3, 4, 5. Okay, so what I'm doing is, let's say this person's height is 1.25 meters or 125 centimeters, corresponding to the 125 volts. Okay,
Mhm.
now I'm choosing this guy as the reference. Okay, and this guy is 130 centimeters. So I'm going to call this guy as plus 5 centimeters
Oh, I see.
above.
Okay.
This is 0, and this is negative 5 centimeters below my reference. So I'm considering this as my baseline.
Okay. Okay, I
Okay,
see. Perfect. All right. Thanks. Thanks.
yep, perfect. So this guy is, I could have chosen any other node as my baseline. Okay, that's a good question. Other questions, please. Okay, let me clean this up. Other questions, please, about setting up the node voltage method, solving using node voltage method. Okay, so you have 3 equations, 3 unknowns. These are the values that you should have seen. V1 is 101.2433 volts. V2 should have been 10.6572 volts. And V3 is negative 106.5719 volts. Okay, did your answers match this guy?
Yes.
Okay, good. So 3 different voltages, but we are not done. All right, so we solve for the node voltages. V1, we know the value of V1, we know the value of V2, and we know the value of V3. So we should be able to calculate any current that I want. I should be able to calculate any current that I want. As a matter of fact, all the currents. If I want to calculate I1, I1 is going to be 125 minus V1 over 1 ohm. Okay, that's I1. Cut that and then place it over here. Okay, so I1. Similarly, you should be able to calculate the value for I2, I3, I4, I5, and I6. Okay, which is simply any current you want to find out. Is I3 is this voltage minus this voltage, so which is V3 minus negative 125, okay, over 1 volt. So this guy I3 is V3 minus negative 125 over 1 ohm. Okay, so applying Ohm's law, the potential difference between the 2 terminals of the device divided by the resistance should give you the current. Okay, questions please, questions so far. And when you solve for these different currents, when you find the value of I1 through I6, they will match up exactly what you got in the mesh current method. Okay, they would match up exactly what you should have seen from the mesh current method. So I might as well copy this and then see the result, paste that as the result that you should see here. Okay, so that's the idea of solving the same problem using node voltage method and mesh current method. Now, that's not the end of the problem. So far, all I have been doing is to give you kind of the big picture, get you started, set up the equations, and then spit out the currents and voltage values for you. That's what I have been doing. But let's see if there is more to this problem. The first part is use node voltage method to find the branch currents I1 through I6. Okay, you sure did find I1 through I6 using the node voltage method. Okay, then there is a continuation to this problem. Test your solution for the branch currents by showing that the total power dissipated equals the total power developed. This is an interesting problem. This is an interesting continuation to the problem. The earlier examples we looked at had the exact same problem, but I did not care to solve that. But here, I want to spend a little bit of time on that, just so in the interest of completeness, I solve just about everything that's asked to solve, that's been asked to solve. Okay, so let's see, how do we test our solution is correct? Okay, one way to check our solution is correct is to verify the power developed, okay, and see if that's equal to the power absorbed. Okay, so now what I'm trying to say is, if you look at this circuit, copy that. So let me add a page here. Part B, verify. Okay, let's see if I can paste this circuit over here. Okay, so you have gotten the values for I1 through I6. Okay, whatever values you got some values for I1, I2, I3, 4, 5, and 6. How do you verify they're correct? Well, one way to verify they're correct is to do the mesh current method. But another technique is to look at all the powers that are dissipated or absorbed. Okay, where is the power absorbed? The power is absorbed by all the resistances. Okay, so if you do this, if you look at all the power absorbed, okay, so you look at the power absorbed in the 1 ohm resistance on the top, which is V squared, which is, we call this as V1, right? Which is I squared R. So I1 squared times R. Okay, look at the power absorbed in the 2 ohm resistance, that is I2 squared times R, which is 1 ohm in this case, 2 ohms in this case. The third power, P, dissipated in the 1 ohm resistance down at the bottom, is I3 squared times 3 ohms, okay, followed by okay. Similarly, the power dissipated in the 6 ohm resistance is I4 squared times 6 ohms. Power dissipated in the 12 ohm resistance equals to I5 squared times 12 ohms. Power dissipated in the 24 ohm resistance is I6 squared times 24 ohms. So if you added up all the powers, all of these, okay, all of these different 6 components, you would get some number, okay? You'd get a number there. Total power absorbed, P total. You'd get a humongous number, okay? 5273.091 watt. 5 kilowatt. Wow, that's a huge number. That's not practical for these kind of resistance and current values. You don't see them in practice, having such small resistance and such large potential values. Okay, so that's one component. In order to find the total power delivered, okay, when you calculate the total power absorbed, okay, by the resistances and the total power delivered by the voltage sources, they should equal the same. Okay, they should equal. Okay, so in other words, if you look at the total power delivered, which is going to be power delivered by the 125 volts source and power delivered by the other 125 volt source. Okay, so this is the power delivered. This is going to be V times power V times I, negative I, right? V times negative I, well, negative of V times I1. Okay, that's the total power delivered by this guy. Okay, what's the total power delivered by the bottom 125 volts resistance? It's power delivered, so negative 125 times I3. Okay, so if you look at the total power delivered by these two sources, you'd see that the power total delivered equals the exact same value, negative 5273.10 watts. Okay, so you see that the total power delivered exactly equals the total power absorbed. Therefore, there is consistency, conservation of energy, and then the total power that is dissipated in the circuit equals to the total power generated or delivered. Therefore, our calculations are correct. So that's one other mechanism to solve for, to verify that our solution is correct. Questions, please. I followed the passive sign convention when doing the power delivered. If the current is opposite to the voltage drop, it's negative. If the current is aligned to the voltage drop, it's positive. Questions, please.
Looks good.
All right, perfect. So let's again catch up on the syllabus really quickly, as is our customary ritual. Let's see. Mesh analysis with dependent and independent sources. And we looked at special cases, some examples. So when we come back tomorrow, we'll spend some time on source transformations. Okay. How can you convert a voltage source with a series resistance into a current source with a parallel resistance, so on and so forth. More techniques to simplify solving. Okay? When you have a circuit, I gave you a bunch of different techniques so far. I'm going to add to that repertoire of your circuit solving skills. Okay, we'll stop here, come back, and take it up in the next class.